포인터 없네.
포인트야.
Today what I would like to introduce is a kind of new endoscopy technique using the fluorescence signal and the Raman signal together. The purpose of using that is we want to see the image using the fluorescence, and we want to see the molecular image using the Raman signal. Let me introduce one by one. This work has been done with the help of many professors, research team, especially Professor Yoon-Sik Lee in chemical engineering at Seoul National University, and also Professor Dong-Soo Lee and Kang in this SNU hospital. With their help, we began this work before around 7 years ago, when recently we can show the result. In the talk, I will introduce this sequence, especially Fluorescent-Raman endoscopic system will be the main topic. And if I have time, a little bit more, then using the same nanoparticle, we can also apply the multiplexed immunohistochemistry application and also multiplexed immunoassay application either. So I hope I can cover all of them. So the starting point of my interest using the surface-based Raman nanoprobe is starting from this kind of simple idea. The biosystem, the number of target is usually huge. For example, protein, we have 20 amino acids, and we have a lot of combination of them. The target is huge. Spectral change is really small, but the functionality is a lot. So we need to use label that recognize that independently. And the label, then how many labels do we need is depending on the number of the targets. So since the target is the number is huge, so we start to find technology to have a large number of the target for one, like the fishing. If we do the fishing one by one, then it takes time. But if we want to fish multiply, then we need to have multi-hole. So if we want to fish the bio-target multiply, then we need to have a multiple probe. For that, I checked basic things, the spectrum, like fluorescence and gold, something like that. Fluorescence and luminescence, the bandwidth is really large within the optical region. But the Raman scattering band is 100 times narrower than this luminescence and fluorescence, or even scattering. So simple calculation gives the 100 times higher number of multiplexing capacity. And if we have combination, it can increase the million or more than million independent proof. But the Raman scattering is basically weaker in signal than the fluorescence and other phenomena. But if we use the nanoparticle like this bottom image, if we have 2 nanoparticles of gold or silver, in the gap side, the intensity, enhancement factor increases typically 10 to the 6 times, and in an optimum case, 10 to the 10 times. This kind of enhancement overcomes the weakness of the Raman signal, and the intensity can be as strong as the fluorescence. So it can be applicable. So there are a lot of research groups that develops the SERS proof by their own technology, and our approach is something like that. We start silicon nanoparticle around 100 nanometer or 150 nanometer, something like that, and then we put the silver or gold nanoparticle in a different way, based depending on our purpose. And this SERS active substrate, and we need to have a Raman label chemical, the red dot here, that has the unique Raman spectrum, Raman fingerprint. And then we cover that with another silica shell. That is the basic unit. We can diverse it in many different ways. Like we can put the magnetic nanoparticle inside, or we can put the fluorescence dye inside either. So we can have a lot of multi-modality. So using that kind of system, we do have a SERS band, and this band can be used for barcode of the bio targeting. So using the material property of silica, the signal is protected inside, and biofunctionality further is very easy, and we can apply any available method for here. So first we showed how many independent labeling is possible. So we published a series of paper, and recently it can be more than 1 million independent barcode is possible. And then where we can use this kind of thing is we can use that kind of thing for high throughput screening, peptide drug or something like that. The peptide drug uses the 20 amino acid and about 5 moles. And it also has a huge lead compound, and we cannot do one by one for this kind of huge number of targets. For that, we can use this kind of proof. And we studied this proof about more than 10 years, and until now, we can have a high sensitivity, similar strong intensity to the fluorescence. So, and also we can check the high quantification ability using that one. Actually, the fluorescence dye has the bleaching phenomenon. The Raman scattering doesn't have bleaching phenomenon, so that is the good advantage, another good advantage for quantification. And also, we are going to have a mass production, and we are also developing the readout system for using the Raman. And also, by putting the fluorescence signal in the SERS dot, we can have additional functionality like fast imaging or cell sorting. Or we can also put the magnetic nanoparticle inside, then we can have separation functionality in there. So we can control various size, and most of the visible region, the extinction is the high, so we can choose any kind of the laser line for Raman excitation. So if we need the NIL, we can just choose the NIL laser and detect. That's it. And also, we want to show the homogeneity in signal, not the size. In signal, we try to particle to the core to satellite structure like that. And then, as you can see in the right corner, the blue dots, the particle intensity is highly monodispersed in a high sensitivity region. So this kind of approach is also available. And this fluorescence sensors proof is the main actor in this study. In this case, the SERS particles are same, but in outer shell, we put the fluorescence dye together like a AF610 dye. Then the particle has the Raman signal here and also fluorescence signal together. So here we use the two kind of the fluorescence source dot. The first signal intensity and wavelength is same, but the Raman signal intense spectrum is different. So we can recognize the type of the particle using Raman signal, and we can recognize the distribution of the particle using fluorescence signal. And that kind of fluorescence dye can be easily applied like the biopsy study. Usually if we have two targets, then we need to make two different slides and staining independently. But in this case, we just make one slide and using two different dye together, and then see the distribution using fluorescence signal, and recognize the type using the Raman signal like that. So this kind of two analysis are done simultaneously. And if we increase the type of the target, then we can have more than 2, 3, 5, 10, more than 10 or whatever actually, the multiple distribution based on using one single measurement. So this kind of thing can be also increased in a high surface screening in two-dimensional. I will not talk this one in detail, but if we use two-dimensional Raman encoding, we can have the 20 to the nth different coding simultaneously. That is there. Just introduction, something like that. And then let me go on the real, the basic, the Fluorescent-Raman study here. So usually endoscopists decide based on the morphology change. And then if they suspect, then they do have biopsy. So later in the molecular, the imaging using IHC, immunohistochemistry, can help the doctor to decide really that is the certain kind of disease or not. But if we do have additional information using the endoscopy measurement, it can have a lot of advantage for the doctors. Like while they do have measurement in the endoscope, if they do have additional information, like where is the HER2 distribution, where is the other kind of PSA or different kind of the biomarker distribution, it is a help for the decision. So how we do is we're using this kind of fluorescent source probe, and it is applied like that. The doctors approach the suspicious lesion in the endoscope, and then they have the spray system in an instrument holder, the normal endoscope, and multiple probes sprayed on the tissue wall of the stomach, then wash out and incubate about 10 minutes. Actually, that is the mouse study data. In human, they may not wait 10 minutes. And then wash out and shine the laser, and the light is collected back to the same fiber optic waveguide, fluorescence and SERS signal simultaneously. And then we optically separate the fluorescence signal to have real-time imaging, and the SERS signal for decode what type of the targets are there. For that, we did also develop the optical system. We didn't develop from the beginning, but we buy one fluorescence imaging system using fiber optic base, and then we assembled our idea with the Raman measurement together. So it goes like that. Lasers are coming in to here, two-dimensional mirror through the optical fiber, bundled fiber, about 10,000 bundles, about 5 micrometer. And sample is here, and the signal is coming back, and then the signal is separated here. So this region, the high wave number region, fluorescence part is passing, and the central region, the SERS part, is passing to the monochromata. By doing that, we can have this imaging and SERS spectrum simultaneously. That is the the image of the system here. So we have this kind of dual monitor system, and that is the simulation. This is the paper, just the paper, and we drop the SERS dot here and approach the fiber optic probe under the dot. Then we have fluorescence imaging and the SERS spectrum together, and off the surface, nothing's observed there. So that is really applied system. That is the model case. The mouse has the post part. The post parts are identical, and this 1, 2, 3, 4 reason we treat it differently. Like this part, we just spray the 2 types of SERS dot here, and we expect 2 types of the signal can be observed. And here we put high concentrate HER2 antibody together, blocking the HER2 part. So the EGFR will appear here, and this part, the HER2 will appear, and this part, nothing will appear. And what we expect is the fluorescence will be shown for site 1, 2, 3, and the SERS spectrum will distinguish 1, 2, 3 either. So that is the result. Here, 1, 2, 3 site fluorescence image is clearly observed in every area. And the SERS spectrum can recognize both of the target appearing in site 1 and site 2. Only EGFR bands appearing in the site 3 for 2 markers appearing, and site 4 nothing can be appeared. So that the same sample was cross-checked with the conventional CLSM microscope. So that is our new finding. And we also applied this kind of fluorescence SERS data for immunohistochemistry of the tissues, especially lung tissues. We did this work with Professor Lee together 2-3 years ago, and that is something like that. The difference of technology is the immunohistochemistry. We need to scan huge image, like millimeter area, and microscope. The beam size or optical region is usually order of micrometers, so it will take huge time. So we developed one reading system. One step is we define the largest subsection, like 200 micrometer by 200 micrometer. Within that one, we do have very fast raster scanning system. And then using the fluorescence, the stages are moving one by one. And if there is a fluorescence signal, then we scan that. If we don't have fluorescence signal, we skip that. In that way, we can cover large area. So if we scan one time, we do have a multiple immunohistochemistry imaging. For that, we do have this kind of long tissue, and we use this kind of high TTF and Neptune staining, and that is the cross-check. And we checked whether the SERS signal also recognize that area really. And then that is there's something before the success, like we didn't succeed the real tissue for the 10 millimeter by 10 millimeter, and we made the mimic system using glass substrate in a 10 millimeter by 10 millimeter, and defined 9 area, and mixing the target different ratio, and then scan one time. And as we expected, using individual SERS band, by one scanning, we do have 3 different distribution of the target. So that is the current stage of the work, and we need further study for the real target. And then I do have a few times, so let me briefly introduce the application of the SERS data for immunoassay of the blood. So concept is similar, and in the 1 drop or 1 millimeter of the blood, we will have a large, different number of targets. And we don't need to say one by one, just we say one spot in a different target together, and just read the source spectrum, and we will have intensity distribution of the marker. For that, we use the PSA at the moment and use the glass substrate, and then we use the sandwich assay like this figure. So conventionally, this SERS dot part, we will have fluorescence dye at the trace antibody, but we use this kind of things. For that, we use the kind of chemistry I will not cover in detail, and we found that each SERS dot about 200 nanometer has about 20 the antibodies around, based on the counting the fluorescence antigen here. And the reading system is something like that. For the kind of the 100 micrometer, 100 micrometer, as you can see the image here, the bright bar will moving. That is just a rest scanning actually. And then we can have a high sensitivity detection. This data shows the multiplex mixing also no problem for intensity correlation with Raman SERS area density and the SERS intensity correlation. And that is the standard curve. And you can see this kind of range here. The circled part is the suspicious region. Over that region, doctors will decide the patient will have a PSA disease, the prostate cancer disease, or they need to do the biopsy, or below that is okay. But that region is quite vague, and there's a need to measure multiple PSA markers like pre-PSA, pro-PSA, and the ratio of them. Then doctors can decide more correctly. For that, there's need to decrease the sensitivity of the measurement. Here, our measurement, the error limit of detection is below pico or picogram per milliliter. Please remember the slope here. You can still see the slope here. And this is the conventional instrument here at this picogram per ml region. That is already flat, already zero. So sensitivity is far higher than our measurement. That is reported the sensitivity of this commercial one. So we do have two order higher sensitivity up to now. And we do have serum data correlation. So it is quite good correlation with the expected value and the measured value in this technique. So this kind of study we can do with the help of the doctors around me and the other engineering collaborators. This is my students, and thank you for them. And thank you for listening.